Modern technology allows researchers studying human motion to collect data on more variables than ever before. However, the outcomes and the quality of outcomes resulting from these data often hinge on the measurement accuracy and often even more so on data analysis techniques following data collection. Take optical motion capture as an example. This is a method of studying human motion that's used in laboratories along with rehabilitation and research and development facilities. And while optical motion capture is quite accurate in measuring the position of body segments, there's still some measurement error or noise. And when we're interested in how those positions change with time, the noise is unfortunately amplified, leaving us with a relatively useless estimate. So researchers studying human motion often deal with this using a filter. You could think of it like a strainer, which works well when the characteristics of the signal that we're interested in are uniform. And further, the characteristics make it easy to distinguish between what we're interested in, the signal, versus what we're not, the measurement error or the noise. In biomechanics, this characteristic is often the frequency content of the movement we're analyzing. Unfortunately, that frequency content can vary throughout time. For example, when there's an impact from running or jump landing, the frequency content can change quite a bit. Further, the frequency content of the signal and that of the noise are overlapped, making it somewhat difficult to distinguish between the two. You could think of this like using a strainer to retain objects of varying sizes, but you're not all that confident in what the size of the object you're interested in retaining is. So I have some plots of a simple example of this. We have circles, which represent the signal, and X's, which represent the measurement error or noise. And the size represents the magnitude of this characteristic that we're interested in selecting for. So on the left, we have our common approach, which uses a single strainer to hopefully select out just the sizes that represent the signal and remove all the sizes that represent the noise. But since they're overlapped, we can see that we're actually allowing some of the noise to remain, and further, we're actually missing some of the signal. So my thesis aimed at addressing this error, and I did so by sectioning out the signal and then applying filters or strainers based on the size of the shapes representing the signal here in this example. And we can see in that lower right plot that this actually represents or results in a better representation of the signal. So using my approach, researchers can be more confident that the results of their data collection represent all of what's actually happening and not so much of the measurement error. Further, since it's objective and automatic, both researchers and non-researchers can readily implement it to inform further research, patient diagnoses and care, performance enhancement, and product development. Thank you.